Hi, I'm Ms. Hearn. Let's get started. In this video, we're going to discuss relations and functions. So to get us started, I want to remind you of what an ordered pair is. So here we have an example of an ordered pair. And remember that an ordered pair has two coordinates, a first coordinate and a second coordinate. We call the first coordinate the x value, or the input, and the second coordinate, the y value, or the output. And it's possible to have a whole set of ordered pairs. And sometimes we represent these ordered pairs in a graph. So for example, the point 4, -7 would be in the fourth quadrant of our XY coordinate system and looks something like this. And we might have a whole bunch of points plotted, like the whole set here of that we're indicating has 3, 4, 2, 5, -1, 5, 4, -7. We could plot each of those points, and that too would represent a relation. Basically, a relation, any set of ordered pairs is called a relation because it defines a relationship between a set of x's and a set of y's. So you can also represent a relation as an equation, like this equation here gives a relationship between x and y values. For example, if I were to plug in the x value 2, we would get 3 times 2 is 6, minus 1 is 5. So we have a relationship between the 2 and the 5, the x and the y value. And we can plug in really anything for x. Like, for example, we could plug in 2.1 for x. So 3 times 2.1 minus 1 would be 6.3 minus 1, which is 5.3. So we see that we have a relationship between 2.1, the x, and 5.3, the y. And I could go on forever listing out an infinite number of ordered pairs, but instead, since I can't actually have time to list an infinite number of ordered pairs, I give a relationship defined by an equation. So our relations might be a list of ordered pairs, or they might be represented by an equation. So if I said, give me an example of a relation in set notation, you might say, okay, I'm going to have the 0.11 and the 0.22 and the 0.33. And those are my set of ordered pairs. Or if I said, give me an example of a relation in equation notation, you might say, I want x cubed plus y squared equals 4. Okay? Any equation that has an x and a y in it. The set of first coordinates in a relation is always referred to as the domain of the relation. That's supposed to be an O there. And the set of second coordinates is called the range. Another way of saying that is that the domain consists of all the inputs, or x values, and the range is all the outputs, or the y values. Oops. All right, so if, for example, I wanted to find the domain of the relation that includes 2, 3, 4, 5, 3, -7, 1, 5, this is my relation, then my domain would be just a set containing all the x coordinates, like 2, 4, 3, and 1. The order doesn't matter. And my range would consist of all the y coordinates, which would be 3, 5, -7. I have 5 again here, but I don't need to list any of the elements twice. It's enough to list them once. 5 is in the range. That's all we need to know. Okay? So that's how we find domain and range. And now we also need to know that in algebra and business calculus and pre-calculus and calculus, if you go either of those routes, most of the relations that we'll work with are actually a special kind called A function. A function is a special type of relation in which each first component in the ordered pair corresponds to exactly one second component. So let's see if this relation that I just jotted down up here, if that satisfies the condition for being a function. So one way to check that is to list out your domain and range and draw little arrows connecting the input to the output. So for example, here we have our domain, that's 2, 4, 3, and 1. Our range was 3, 5, and -7. Looking back at the ordered pairs up here, okay, we're going to draw arrows connecting each input to its output. So 2, the input 2 leads to the output 3. The input 4 results in the output 5. The input 3 results in the output -7. And the input 1 also results in the output 5. So is it the case that each first component corresponds to exactly one second component? Or another way of saying that, which I think is really important to understand, is this relation a good predictor? If I tell you the input, do you know the output without any uncertainty? So for example, if I say the input is 2, you know the output's 3, right? If I say the input is 4, you know the output is 5. There's no other number it could be. There's no additional second component. If I say the input is 3, the output you know is -7. If I say the input is 1, the output you know is 5. Doesn't matter that the input matched up, the input 4 and the input 1 both matched up with one single output, because we were not told that the second components could only be matched up with a single first component, only that the first component can only be matched up with one output. So this actually is a function. It's a good predictor. Let's look at an example from my math lab now. So here we're asked to determine whether the relation is a function and give the domain and range. I like to start with the domain and range, so let's jot those down, right? Because then we can use that to draw our little arrows. So the domain is going to include any first coordinates or x values. There's only 2, the 1 and the 2. Okay, so that's our domain. The range includes 4 and 9. These appear more than once, but we don't have to list them in our set more than once. All right, now let's draw arrows matching inputs with outputs. So the input 1 matches up with both a 4 and a 9. The input 2 matches up with both the 4 and the 9. All right, so is it the case that for each single input there's only one output? No. Right here we could have stopped and said, well, 1 matches up with 4 and 9, so that violates that. Another way of saying this is that this relation is not a good predictor. If I just tell you the input and don't specify the output, you're not sure which output I'm talking about. If I say the input's 1, well, you don't know if I'm talking about the output 4 or the output 9. So this is not a function. It's a relation, but it's not that special kind of relation that's a good predictor, not a function. All right, let's look at this one down here. We have the same instructions, so I'm going to go ahead and list out my domain and my range and see if we have a function. So the domain includes all the x values, so we have -5, and we have 5, and we have 7, and we have -7. Okay, that's our domain. And our range, let's see, we have -2, we have -7. Remember, you don't have to put these in any particular order. Here we have 7, and we already took care of -7, so there we go. So now I'm going to match them up, and we're going to have -5 matches up with -2, 5 with -7, 7 with 7, and -7 with -7. So is this a function? What do you think? For each input, do we have exactly one output? that it matches up with. Is it a good predictor? Yes. No matter which of these elements of the domain I mentioned, if I said the input, for example, is 5, would you have any question about what the output is? No. You would know it's -7. That's the only option. So this guy is a function. Okay, so just take a note. This one was not a function. And this one was a function. When you're looking at a list of ordered pairs, if you don't want to go through the process of drawing the arrows, a shortcut is you can see that the input is listed twice. It has to be because it's matched up with 2 outputs. So you know you don't have a function when you see a relation given in this format when the first coordinate appears twice. The same first coordinate appears twice. Okay? You do have a function if no first coordinate is repeated. And I shouldn't really maybe even say appears twice, because it would also not be a function if it appeared 3 times or 4 times. So maybe I should say same first coordinate appears more than once. It's okay for the second coordinate to appear more than once, but not for the first coordinate. Okay. So now let's see what happens when our relation is represented as an equation instead of as ordered pairs. So the same idea goes, we want to make sure that for each x it matches up with only one y. Each input matches up with only one output. Each element of the domain matches up with only one element of the range, however you want to say it. But the way we check that is different because it's given to us in a different format. What you do is you solve for y in the equation. So in this case, that would mean subtracting x squared over to the other side. So y equals, you could either say -x squared plus 36 or 36 minus x squared. But in any case, if I were to take a number, any number, and by the way, the domain of this equation is all real numbers because you're able to plug any real number you want into it and it makes sense. So if I say picked the number 1, then I would have -1 plus 36 is 35. I'd get one answer, right? The 1 would lead to the number 35. If I were to plug in 2, I'd get -4, which would give me 32. -4 plus 36 is 32. It's never going to be the case that I get anything other than one answer, right? When you square a number, negate it, and then add it to 36, you always get one answer. So this is going to be a function. So you might say, Ms. Hearn, won't that always happen when you have an equation and you solve for y? But the answer to that is no. Let's take a look at a situation where it would not happen. So here we have, I'm going to scooch this up just a little bit. Okay. So here we have x squared plus y squared equals 49. I'm going to do the same thing. I'm going to solve for y. And that means, again, moving the x squared. So y squared equals -x squared plus 49. And then y is not completely by itself yet, though, is it? It's squared. And remember, we use the square root property to get y by itself when it's being squared. So if y squared is equal to -x squared plus 49, then y itself could be plus or minus the square root of -x squared plus 49. So what does that mean? If x were chosen to be 1, for example, then that would mean that we would have -1 squared plus 49 is 48, and our answer would be plus or minus the square root of 48. We could simplify that, but to save time, I'm not going to, because I'm just trying to make the point that there are 2 results, a positive and a negative, as our output. So that's 2 outputs based on 1 input. And so if that can ever happen, this is not a function. It's not a good predictor. If I tell you the input is 1, you don't know which output I'm talking about. So this is not a function. And in fact, this will happen anytime you solve for y and you have a y squared here. In fact, it's going to happen anytime you have an even power on the y. Y will not be a function of x in that case. It's okay for x to have an even power. We saw that in the previous example up here. But it's not okay for y, because then that means that there's a single x that can give two answers, two outputs. If you think about it, there's another situation that we know about where you'd get more than one answer. So you got to watch out for that too. If you had something like absolute value of y, right? So if you were to solve this equation, you'd get absolute value of y equals 3 minus x, or negative x plus 3, however you want to write it. And this translates into two equations. To get rid of that absolute value, you would have to consider both cases. Either y is the positive version of 3 minus x, or y is the negative version of 3 minus x. And so two outputs again. So not a function. So those are the things you mostly want to look out for when y is raised to an even power or an absolute value. Y is in an absolute value, then you do not have a function. Okay? All right. Now let's talk about what if our relation is given to us not as a list of ordered pairs or as an equation, but as a graph. So if we have a graph, then we're going to use something called the vertical line test. So let me explain, before I write the vertical line test out in words, let me explain to you visually what it means. So here it says, use the vertical line test to identify graphs in which y is a function of x. What I want you to think about is the input and the output idea. So here, let's say this is the number 1. They didn't actually give us a scale on this graph, so I don't really know, but pretend for a minute that this graph has a 1 here. That means that the input, the x value is 1, corresponds to two different ordered pairs on this graph. Maybe this is the point 1, 3, and this is the point 1, negative 5. I don't know. But the point, it doesn't really matter what the actual values are. What matters is that this input matches up with more than one output. And that's always going to be the case when you have them vertically one above the other. So in other words, if there is a vertical line, let me type this out. If there, oh, this is tiny. Let me make it bigger. If there is a vertical line that can be drawn through any part of the graph of a relation that hits more than one point on the graph, then the relation is not a function. Okay, so in this case, we definitely do not have a function because it hits more than one point. So that gives you a really quick way to check. What we say is that this guy, since I hit more than one point on the graph, oh, and my graph moved, so that's funny. Let's erase that. Since I hit more than one point on the graph by drawing a vertical line, oops, sorry. By drawing a vertical line through this relation, I hit more than one point on the graph. This fails the vertical line test, VLT, vertical line test. Okay, so let's look at the next graph. All right, so for the next graph, try to imagine drawing vertical lines through the graph anywhere you want to. Oops. Okay, there's another one, and there's another one. I can keep drawing vertical lines forever. Is it ever the case that this function is folded over itself where we're going to hit more than one point? No. So this one passes the vertical line test. All right, so whereas the one above was not a function because it failed, this one is a function. It passed the test. And let's do one more here. All right, this is an interesting one. It has two pieces. This relation has two pieces. This is called a piecewise defined relation, and we are going to see if it's a function. So imagine drawing vertical lines through the graph. No matter where I draw those lines, isn't it the case that it's only going to hit one point? Right? So this one passes the vertical line test. Oops. VLT, not LLT. VLT, vertical line test, and so this is a function. So we've seen that our relations can be given to us as a list of ordered pairs, as an equation, and as a graph, and we have tests for all three to determine if it's a function. You can always rewind the video and watch the other two again to refresh your memory. And I'm sure there's other YouTube videos explaining the same idea if you want to find a different professor's explanation. But now we're going to move on to function notation. So when we know we have a function, we often use this notation f of x to represent the y value. And it's read f of x or f at x because what it represents is what is the y value when you plug in a number, a particular number for x, right? So let's look at this example. Instead of writing the equation y equals 3x plus 1, I've written the equation f of x equals 3x plus 1. Now, one unfortunate thing about this notation is it looks like I'm multiplying some variable f times x, and that's not what it is at all. So this is supposed to indicate that we're plugging in a certain number for x into our function, which we've given the name f. Okay, so for example, let's look at f of 5. What does that mean? That means that we're plugging 5 into the equation into the expression 3x plus 1. So 3 times 5 plus 1, which gives us 15 plus 1, which is 16. So you could say f of 5 is 16. This is another way of saying that when x is 5, y turns out to be 16. So if we were to graph this guy, we would have the point 5, 16 on our graph. Okay, but we can plug other things besides numbers. We can plug variables in. And we could say 3 instead of x, we're going to put a plus 1. So f of a is 3a plus 1. We could plug a box in, a placeholder. So f of the box is 3 times the box plus 1. And I like to emphasize that you can put anything you want in that box, right? So for example, I could put, in that box, I could put a heart. So 3 times heart plus 1. In that box, I could put myself. So f of Miss Hearn equals 3 times Ms. Hearn plus 1. Anything you put in these parentheses is going into this box, this placeholder. All right, so the type of question you're going to see in our class in my math lab would be like f of x equals x squared plus 2x plus 9. That they're telling you is a function. That's why they're using function notation. And at the given values, we're supposed to evaluate that function at the given values of the independent variable. By the way, the x, the input, is sometimes referred to as the independent variable. And the output, the y, is the dependent because it depends on what you input. So if you see independent and dependent, they're just talking about the x and the y. All right, so, and then simplify. Okay, so let's start with f of 1. So remember, my original function was f of x equals x squared plus 2x plus 9. And each of these x's is really just a placeholder. What I mean by that is we can put anything we want in there. So think of it as a box. Whatever we put in there, we're going to square it and we're going to multiply 2 times it, and then we're going to add 9 to it, to our box. Okay, whatever's in the box. So what if I put, for part A, I'm putting a 1 in the box, right? So I'm evaluating 1 squared plus 2 times 1 plus 9 for part A. F of 1 equals 1 squared plus 2 times 1 plus 9. So that's going to be 1 plus 2 plus 9. Remember, multiplication comes before addition, and exponentiation comes before multiplication or addition. All right, so we're going to have 3 plus 9 is 12. So f of 1 is 12. By the way, we were not asked this in this exercise, but that means that if we were to graph this relation, this function, we would have the point 112 on the graph. Part B, they're asking us to plug in x plus 3, and people find this very confusing. I'm going to give it a different color to emphasize that we're plugging it in. All right, so what are we really doing? We're putting it into that box that I talked about. Don't think of it as an x, think of it as a box. All right, so we're plugging in a box. F of whatever equals whatever squared plus 2 times whatever plus 9. Make my boxes clearer here. Okay. All right, so what's in the box this time? X plus 3. So we're going to take that guy and we're going to plug him in. And whatever we plug in, we square it, we multiply it by 2, and we add 9 to it. So I'm going to take that guy in my box, x plus 3. I'm going to square it. I'm going to multiply it by 2, and then I'm going to add 9 to it. Doesn't matter that it has an x in it. It's not the same x that you had up there, so don't get confused by that. So what are we going to do? X plus 3 squared. So we have to square a binomial. So we're going to have first term squared, x squared, second term squared, 9 squared, and twice their product in the middle. So that's going to be plus 6x. Remember, square the first, square the last, multiply together, which is 3x, and double up fast gives you 6x. Oh, not 9 squared, just 9, sorry. 3 squared. 3 squared is a 9. All right, and then plus 2 times x plus 3, so distribute 2x plus 6 plus 9. And so we get, combining like terms, x squared plus 6x plus 2x is 8x. Plus 9 plus 6 is 15, plus 9 is 24. All right, so that's about as simplified as we can get. So what is that telling us? That's telling us anytime we plug in a quantity of the form x plus 3, the output, the corresponding y coordinate would be x squared plus 8x plus 24. Okay, but all you need to put into my math lab is the answer here. Okay, part C. So this time, what are we plugging into the box? We have f of negative x. So negative x is going into the box. Okay, so let's draw our little boxes here. What are we doing to our boxes? We're squaring them, multiplying it by 2, and adding 9. And what's going in the box this time? Negative x. So we're going to get negative x squared, the quantity, the whole thing's being squared, so that turns it to a positive x squared. 2 times negative x is negative 2x plus 9. Okay, so, oops, I don't like that circle. So that's how we would plug negative x into that function. Okay, so that's function notation. And I'm sure you could probably run a search on function notation and find a lot of YouTube videos with different professors explaining what function notation is, how it's read, and how to work with it. Now we're going to talk about graphing functions by plotting points. Okay, so this is a My Math Lab question in our book. It comes from Chapter 2, Section 1. It says graph the given functions f and g. So it's not only f of x, we can actually give any letter name. We commonly use g, h, j, k. So f of x and g of x are, when we have to talk about two different functions in the same scenario, then we'll give two different names so we can distinguish between the two. It's sort of an advantage instead of having to use y equals negative 4x and y equals negative 4x minus 5, where we might get the two y's mixed up, right? So, but really, these two notations are just y values, okay? All right, so we're going to plot points. Plotting points is not the most efficient method of graphing. But when you're first getting used to certain, new equations that you're not familiar with, we often use plotting points to just get a feel for them. You probably already know, you should know that these are lines, y equals negative 4x and y equals negative 4x minus 5. You might also recognize their slopes are both negative 4, and so they should be parallel lines. But we're going to be graphing functions you're not familiar with in this section. And in that case, what I want you to do is I always want you to plot a few negative values, 0, and a few positive values, unless I tell you in the instructions, I tell you otherwise, because there will be functions like the square root function where you can only plot 0 and up or whatever. But if I don't tell you, just make a little XY chart and plot like negative 2, negative 1, 0, 1, and 2. Or you can do more on either side of 0, but make sure that you at least do a couple negatives and a couple positives and 0 itself. All right, so this is our XY chart, but we're not calling it Y anymore, are we? We're saying we have a function, so we can call this f of x. And what does f of x tell you to do? It tells you to take your x, whatever it is, and multiply it by negative 4. So if I plug in negative 2, we're going to get negative 4 times negative 2 is positive 8. Plug in negative 1, negative 4 times negative 1 is positive 4. 0, we get 0. 1, we get negative 4. Multiply 2 times negative 4, we get negative 8. Okay, so let's go ahead and plot f of x. I'm going to plot him in blue, I guess. So we have 0, 0. We have 1, negative 4. I like to label my coordinates unless they're on the origin. 2, negative 8. Okay, we have negative 1, 4. And we have negative 2, 8. And then we're going to put a line in there. We know it's a line in this case. I gotta scoot him over here. All right, that's pretty close. Okay, so that's f of x, and now maybe in red we'll plot g of x. But again, I want to use a couple negatives, negative 2, negative 1, 0, 1, and 2. So g of x takes this number and plugs it into negative 4 times x minus 5. So for each of these numbers, we must multiply by negative 4 and then subtract 5. So for negative 2, we have negative 4 times negative 2 minus 5. That's going to be positive 8 minus 5, which is 3. For negative 1, we're going to have negative 4 times negative 1 minus 5. So that's going to be 4 minus 5, which is negative 1. For 0, we get negative 4 times 0 minus 5. That's going to be negative 5. Let's see. Oop. For 1, we get negative 4 times 1 minus 5, which is going to be negative 4 minus 5 is negative 9. And for 2, we're going to have negative 4 times 2 minus 5 is negative 8 minus 5, which is negative 13. All right, so just to be clear, what are we saying here? We're saying that our function g goes through the point -2, 3, the point -1, -1, the point 0, -5, the point 1, -9, and the point 2, -13. If you need to, you can, oh, I'm a little over there. You can pause the video and try and graph this on your own, just and then resume the video so that you can be, following along. All right, so -2, 3 would be here. Okay, -1, -1 would be here. And then 0, -5 would be, oh wait, no, I just plotted -1, +1, excuse me. Thought that looked a little off. Come on eraser, work for me. There we go. All right, -1, -1 would be here. 0, -5 would be here. 1, -9 would be here. And 2, -13 would be here. Okay, and then we're going to put in our line. And this is a little crooked. Let's see if I can get it straightened out. Okay, pretty close. All right, and this guy's a little crooked too. Ah! Can't get it straightened out. All right. Basically, though, we know from what we know about lines that these two are supposed to be parallel. So they're supposed to be going at the same slope. I'm just having trouble drawing it. Oh, there we go. That's better. Okay, so these two lines are parallel. One of them is just lower than the other one. In fact, the red line is, oh, no, you can't tell because that one goes through 0, 0, but it's hard to see there. Okay, the red line is just 5 units lower. 5 units lower than the blue line. And there's a reason for that. It's because we subtracted 5 from every y value. So that's why that happened. Okay, so that's how to plot functions by, or graph functions by plotting points. Let's look at a function that we're not familiar with. And again, since you might be familiar with this shape, but you might not. So I'm going to assume you don't know anything about it, and we're just going to plot points. And whenever you don't know, you just start with some negatives, some positives, and 0. So I'm going to go ahead and plot for f. We have the x, and then we have the f of x, or y, which is equal to negative x squared, the opposite of x squared. So if I plug in -2, -1, 0, 1, and 2, let's see what I get. So I'm going to have, remember, this is like a box that we're plugging that number into. So we have negative and then -2 squared. So that's going to be the opposite of 4, so -4. And then if I plug in -1, negative of -1 squared is going to be negative, our opposite of -1 squared is opposite of 1. And if I plug in 0, I'm just going to get 0. If I plug in 1, I have the opposite of 1 squared is -1. And if I plug in a 2, I have the opposite of 2 squared is going to be -4. Okay, So plotting those points, we have, I always like to start with the 0. 0, 0. All right, and then we have negative 1 would be about here. And 1, negative 1 would be over here. So that's negative 1, and that one would be 1, negative 1. And then we also have negative 2, negative 4 would be here. Negative 2, negative 4. And 2, negative 4 on the other side. Okay. Oh, come on. Okay, so connecting the dots, it looks something like this. Now, one thing that you should know is all polynomials, any function that's a polynomial, is going to be a nice smooth curve. There aren't going to be any sharp points. So this is going to be more shaped like a U, an upside down U, rather than say like an upside down V. It won't have a sharp point in it. Okay, now let's look at g of x equals negative x squared plus 10. So I'm going to make an xy chart, but it's x g of x, and g of x turns x into negative x squared plus 10. By the way, in case it's confusing you, this squared is only affecting the x, not the negative, which is why these things didn't change to positives up here. In order for the squared to affect a negative, it would have to be in parentheses, like negative 2 squared would be positive 4, for example, but that's not the situation that we have. All right, so we're only squaring, there's no parentheses, we're only squaring the x part. Okay, so if x is negative 2, negative 1, 0, 1, and 2, let's see what happens. Plugging in negative 2, we get the opposite of negative 2 squared plus 10. So that's going to be negative 4 plus 10, which is 6. If we plug in negative 1, the opposite of negative 1 squared is negative 1 plus 10 is going to be 9. And if we plug in 0, we're just going to get 0 plus 10, which is 10. If we plug in 1, we get negative 1 squared plus 10, which again is 9. And if we plug in 2, we get negative 2 squared plus 10, which again is negative 4 plus 10, which is 6. So what we're really saying is that our new function g goes through negative 2, 6, goes through negative 1, 9, it goes through 0, 10, it goes through 1, 9, and it goes through 2, 6. So let's plot those points. So I like to start with the 0, 0, 10 would be up here. And then negative 1, 9 would be about here. Negative 1, 9. And the only reason I'm making little x's is just because it's a flaw in the program. When I make a little dot, sometimes weird things happen. So it should be a dot, not an x, but for technical reasons, I have trouble making dots. All right, and then this would be 1, 9 here. And then negative 2, 6 would be about, let's see, negative 2, 6 would be about here, and 2, 6 would be about here. Okay, so connecting the dots then, it's again the same type of shape. By the way, it's going to go forever downward. If I kept plugging in values of x, more x values, I would get lower and lower y values. All right, so what we see here is that the green graph, which remember was g, and the blue graph is f, that g is 10 units above f, but the same shape. Okay, and the reason that happened? Well, because the only difference is we're adding 10 to every y value. Okay, so when you're asked to graph functions by plotting points, unless you're told otherwise, I want you to use these x values, or you could use like negative 4, negative 2, 0, 2, and 4 if you wanted to spread it out a little bit. But a couple of negatives, 0, and a couple of positives will be your best bet for getting the shape that you need. Also, graph on paper first, And then when you go to put it in MyMathLab, once you have it on paper, you'll know the basic shape. So like here, you'll be able to use, oh, it's kind of a U shape. And you'll be able to select the right shape to graph in MyMathLab. But first, you have to graph it on paper. And remember, on the test, I will make you graph it on paper. So you want to practice that. That's a separate skill from graphing in MyMathLab. Okay, now we're going to talk about when we're given a graph, how do we read information about a function off of the graph? So in this case, we're given this graph in MyMathLab. This is 2.1.67, so this is still section 2.1. We want to use the graph of f to find the value of f of 2. So what on earth does f of 2 mean? Okay, so you remember we have some equation for f, but they're not telling us what that equation is. They're giving us the graph instead. Okay, and so remember that when we plugged into that, we plug in the input x, and we got out the output, which was our y value. So this guy is our y value. X is the input, the output is f of x or y. All right, so when they ask you to find f of 2, what are they really asking you? They're asking you what is y when x is 2. Or another way of saying that is, if you put in the input 2, what is the y coordinate? Because the input 2 is matched up with the output that goes with 2, f of 2. So we're really looking for that y coordinate. So how do we find it? Well, we go to the x value 2 on our graph here, and we just look up to see what pair of coordinates that matches up with. So that's going to be the coordinate 2 in the x, but look, it's also 2 on the y. So the answer is that f of 2 is equal to 2. All right, or in other words, it goes through the point 2, 2. So when we're given function notation, we need to understand what that means on a graph. All right, let's look at this one. G of 3. Okay, what is g of 3 equal is the same as asking when x, this is always your x, inside the parentheses, and the y is the whole thing. Our x is 3, we're looking for our y, our g of x. Okay, g of x is just y. It's another notation for y. So we look at the graph and we find the x value 3 right here between 2 and 4. And we look down at what's corresponding to that on the graph, that point right there. What are the coordinates of that point? Well, 3 obviously is the x coordinate. That's how we found it. But the y coordinate is -8. So the answer here that we would type into MyMathLab would be -8. Hope that makes sense to you. All right, now look at this one. This is slightly different. They're not saying what's g of 5. They're saying for what x value is g of x equal to 5. So here they're asking us to find the input, the x coordinate. In other words, we know that there's some pair of coordinates on this graph that has an input of unknown input x. We're looking for that. But the output is 5. The y value is 5. The g of x value is the y value, it's 5. So we're going to go to the y-axis and we're going to look for 5, which is here. And we're going to look across both sides and we see the only point that has a y value of 5 is this guy right here, something 5. What is that something? Well, let's look down here. Oh, it's -8. That's a coincidence that it was the same as in the last problem. That's not always going to happen. All right, so the x coordinate of that point was -8. So the x value that we're looking for, -8. Okay. All right, here we're being asked to find several things. The function's domain, the function's range. By the way, we know it's a function, right? Because it passes the vertical line test. We could draw vertical lines until the cows come home, and we're still going to only hit 1 point, never more than 1 point. You remember us talking about that? All right, so that's why they're referring to it as a function. When we talk about domain, we're talking about the x values that the function has in its set of ordered pairs. But we're not given the set of ordered pairs or the equation, we're given a graph. So we have to determine wall to wall what x values this is going to hit. Now keep in mind the arrow is indicating it's going to continue, right? So what's the furthest point to the left on this graph? The furthest point to the left, well, there isn't one. It goes on forever out to negative infinity. So the domain is going to include all the numbers out to negative infinity. And then what's the furthest point to the right? Again, there isn't one. It continues onward, so it goes out to positive infinity. So if we were to, one way we could explain this is to say that the domain is all real numbers. Or in interval notation, how do we describe a set that goes on the number line all the way from negative infinity to infinity? We would say interval parenthesis, negative infinity, comma, infinity, close parenthesis. Okay, so that's the domain. Now let's analyze the range. Range is y values, which would go bottom to top, right? And again, this is going to continue downward. But it doesn't continue upward. There's going to be a no lowest point, but there's definitely a highest point. So our y values go from down here at negative infinity up to the highest point, which the highest point on this graph is this point. What are the coordinates of that point? It appears to be the point -1. I'm sorry, that's the y value. It appears to be the point 4, -1 maybe. Let's look closely here. Kind of scribbled over it. Yeah, 4, -1. All right, so if that's the highest point on the graph, 4, -1, what's the highest y value? Well, that's the -1. So what we're saying is that we're going all the way from negative infinity up to -1, from here to here. Each one of those y values exists in one of the points on this relation. For example, or function, I should say. For example, here's the point, looks like 7, -4. So the -4 is one of the y values between negative infinity and -1. Here's the point 0, -5. -5 is another one of the numbers between negative infinity and -1. But we can't list them all, so we can use we have different options, but in interval notation, this would be negative infinity up to -1. And we're actually including the -1 because there actually is a point on the function with a y value of -1. So we're going to have a bracket there to indicate we're including that point. Okay, so that was part B. We were finding the range of the function. Now let's find part C, x-intercepts. So x-intercepts are points where the function hits the x-axis, but there are none on this one. So for part C, we would say none, no x-intercepts. And y-intercept, if any. So y-intercept is any point where the graph hits the y-axis. We see that happens here at 0, -5. So the y-intercept, part D, is going to be 0, -5. Or in my math lab, they might just ask you for the number -5. I'm not sure. But technically, it's a pair of coordinates with the x-coordinate being 0. All right, and now they ask us for function values f of 3 and f of 5. All right, so let's start with f of 3. Remember, that's telling us we're plugging into f the x value 3. So let's go to our graph and figure out if any of the points have an x value 3. So here, about here would be 3. Oh yeah, look, the graph has a point down there that has an x-coordinate of 3. What does it look like? It looks like it's 3, 1, 2, negative 2. So f of 3 is negative 2 is another way of saying it goes through the point 3, negative 2. And now let's find f of 5. That's another question in part E. All right, so I'm going to erase this stuff again. I'm going to go over to 5, go down here. We see that it does hit the graph. And it looks like 5 also has a, when x is 5, the y-coordinate appears to also be negative 2. So the answer here is also negative 2. Okay, so there is a lot of information we can get from the graph. And when you are asked questions about a function, you know, your approach is going to be different if you're given the list of ordered pairs, or if you're given an equation, or if you're given a graph. Let's look at one more question, and let's see. So again, we have a new function here. We're asked for the function's domain, range, x-intercepts, y-intercept, and the value f of 2. So let's start with the domain. So domain is the x values, and you'll see we want it when we're doing x values, we're going furthest point to the left to furthest point to the right. So here's the furthest point to the left, here's the furthest point to the right, and I'm gonna kind of project it down to the x-axis. So here is this pair of coordinates appears to be 0, negative 1. And this pair of coordinates appears to be 3, 8. All right, so when we're talking about domain, we're talking about x values. So the furthest point to the left has an x value of 0. The furthest point to the right has an x value of 3, and we want everything in between. Are we including 0? Yes, because there's a closed dot. We actually have a point on the graph, 0, negative 1. But this open dot here indicates 3, 8 is not actually a point on the function. It's a boundary, but we don't actually hit it. So we're going to indicate that on our interval that 3 is not actually in our domain. It's just a boundary of it. So we're going to put a parenthesis there. Okay, so left to right, wall to wall is our domain. And now let's find our range. Thinking bottom to top or floor to ceiling. We're going to go the bottom of it to the top of it, right? So we hit every point in between, which means we're going to hit every y value in between. In between what? Well, this again was the point 0, negative 1, and this was the point 3, 8. So the lowest y value this time is negative 1. And it goes all the way up to the highest y value, 8. You got to go in numerical order, left to right in interval notation. All right, now, are we including negative 1? Yes, because again, that's a closed dot. Are we including 8? No, because it's an open dot. Okay, now let's find the x-intercepts, if any. So we look across the x-axis and we see if the graph intersects it, which it does. And it does so at this point here, which appears to be the point 1, 0, right? And so our x-intercept is 1, 0. By the way, you should always have a 0 for your y-coordinate of your x-intercept and a 0 for your x-coordinate of your y-intercept. All right, so let's find the y-intercept if there is one, which there is. We see here. Let me erase this. So looking along the y-axis this time, we definitely intersect the graph at the point 0, negative 1. So that's going to be our y-intercept. 0, negative 1, 0, negative 1. And now let's find f of 2. And again, if I'm going too quickly, you can pause the video, rewind it. F of 2, we're looking for the x value is 2. What is the y value, right? So we're looking for a pair of coordinates to something. So we go over to 2 on our x-axis. We go up to the graph. We see we do hit something there. What do those coordinates appear to be? 2, 1, 2, 3. So it looks like f of 2 is 3. It goes through 2, 3. So the missing unknown y value is 3. Okay, so that ends chapter 2, section 1 for my class. We've talked about relations, functions, the definitions, domains, ranges, graphing functions by plotting points, function notation and plugging into it, and how to read information about a function from a graph. I hope you found this video helpful. If you did, please remember to like it, give it a thumbs up so other students can find the video.